Good afternoon and welcome everybody, and welcome to this webinar that we have reporting on the findings and innovations explored during the Ethiopian mini-grid extension and energy storage project. This project was funded by Innovate UK as part of the Energy Catalyst Round 7 starting last year and completing this year very shortly. We've got a wide range of presenters today. We've got Simon Igufose from Pyrogenesis, and project partners Andy Gill from Cpl, Christiani Scalda Ferry from Aston, Mary Black and Juma Sadukan from the University of Surrey, Hilawe Tesema from Ethio Resource Group out in Ethiopia, and Laura Alliston from Acceleron. And I'll be introducing everybody in the webinar. So during the webinar, there'll be a chance for anybody to ask questions for us on the technical side of the webinar, or for the presenters, any technical questions that you have from them. And indeed, floating questions for people to discuss during the Q&A session that we'll have at the end. So if you want to ask any of those questions, please use the Q&A tab that you should have down the side of your screen. And indeed, because part of the purpose of today's webinar is to introduce you to the different project partners who've been working on this in this area. So if you want to contact any of the presenters or make contacts with any of the project partners afterwards, please do email us at the contact address that was in your confirmation emails for the webinar, and we can always route those contact request emails on to the different organizations presenting here today. So my name is Bernie Jones, and I run an organization called Smart Villages Research Group. Since 2012, we've been looking at new ways to achieve energy access and rural development around the world. Now, the model that we came up with is a holistic one. So it's using an integrated approach so that we don't just tackle energy itself, but we look at all of the challenges that a community might be facing in the round. So anything from employment, education, health issues, even infrastructure issues that they might be having. And we try to work with the community to implement sustainable solutions across the board. So energy then isn't an end in itself, it's a catalyst for all of these other sorts of things. I first met Pyrogenesis and came across their technology 2 years ago, actually at a meeting in Ethiopia. And I was really struck at the time by how well their technology lends itself to an integrated approach. With just one piece of machinery, it actually fulfills quite a lot of these different aspects of rural development. So that's one reason why I was so interested in the work that they've subsequently been doing with their partners. And it's been my pleasure really to follow the activity in this project over the last year, to see how all of the different partners have been bringing together these diverse approaches and diverse technologies to try to achieve an improved approach to energy access for Ethiopia. And of course, because a lot of this technology generalizes itself very well, also elsewhere in sub-Saharan Africa. I can remind you that this is a very timely work for Ethiopia. Less than 25% of the rural population of Ethiopia has access to quality electricity. And the Ethiopian government is well aware of this and has been, for the past couple of years, publishing a series of strategies and policies trying to encourage the development of mini-grids for rural energy access. This report that I've highlighted here from the Ethiopian government's website is just one of the latest reports that they've commissioned on some of the standards and feasibilities studies for mini-grids in Ethiopia. So the time is absolutely right for new approaches of the sort that are going to be discussed in this webinar to improve the performance of mini-grids and improve the way that mini-grids can impact rural populations. Now, before we start the webinar, we would like to run a couple of polls for the audience, just so we can find out a little bit about who is listening to us today, and maybe think about how some of the presenters tailor their presentations to the audience that we have. So the first question that we are going to ask you is where in the world you're joining us from. So I'm going to start that poll now. If everybody can click on the appropriate buttons on their screens to tell us where you're coming from. And we'll leave this up for a few more seconds so that people can click on it and the results can come through. And publishing the results now. So we're a little bit early in the morning or late in the afternoon or evening for our colleagues in the Americas and Asia at the moment. Most of our participants are from Europe, but we have got some participants at the moment joining us from Africa, which is very encouraging. And if the statistics for our previous webinars are anything to go by, just some of the bandwidth challenges in Africa means that a lot of our participants from Africa ended up joining us a few minutes later. So hopefully those numbers will increase. The second poll that we would like to run is what your interest is in this subject matter. You know, what sectors are you working in at the moment? So again, those questions are up on your screens at the moment. If you'd like to click the appropriate buttons, then one of our presenters will know who they're talking to. We'll leave this up for another 5 or 10 seconds. Okay, I think that's all the answers that have come in now. So we'll publish this result as well. So about half of our audience is from the research sector. About a third is from the corporate sector, but we do have some people from the general public, which is always good to have. And also that means that those of our presenters who are talking about technical things will be making sure that all of the technical material that they're presenting is accessible to everybody who's listening to us. So that's great. Thank you very much for participating in those polls. As I said, if you can ask any questions that you have in the appropriate section, we'll either answer technical questions during the webinar or the questions to our presenters we'll deal with at the end in the Q&A section. So without any further ado, I would like to invite Simon Igufose, the Chief Exec of Pyrogenesis, and indeed the project manager of this project, to tell us about the work that you've been doing, Simon.
Hi there, Bernie. Thanks very much. Can you hear me okay?
I can.
Okay, right. So I'll just share my screen so that I can get my slides up. Okay. Right, correct tab. Okay. There we are. Can you see that in full presentation mode?
Just coming up. Yes, we can. That's fine.
Okay. Brilliant. Right. Okay. So firstly, I'd just like to thank University of Leicester for hosting me today in the Leicester Innovation Hub. You know, that was very handy having such a facility like this. So thank you very much. Thank you for all our guests who are joining us from all the various parts. It's really good that you're here today and that you've got this interest in the work that we've been doing. This has been a great consortium to be part of and has produced some exciting results, which our partners are going to tell you about. So today, I'm going to be talking a little bit about our technology and how it really provides a solution for the setting that we find in Ethiopia. And what I'd like to say as well, before I get started, is that the purpose of this call and this webinar is that we're looking to, and people who have joined this webinar, we're very much interested in collaborations with you, whether that's commercial collaborations, especially if you've got capabilities in Ethiopia. We'd very much like to talk to you. And so if you see something that you think, yeah, that's something that you can be part of and want to get involved and engage, please do contact us through the website. So the Pyrochemic Process, it's a pyrolysis-based technology at a containerized scale. So typically we're converting about 2,000 tons of agricultural waste per year. And we use pyrolysis, which is an advanced thermal technology that heats things in the absence of air to act as like a separation process. And so that separates into like a vapor phase and a solid phase. The solid phase is what you see down here, which is called biochar. And this is called biochar because, of course, we're using waste biomass. And it has to be a waste. We don't want to be competing with, commodities or anything that people are already using and have a market for. So typically, this diagram is actually quite good. You can see all the useful stuff is underground. You'd eat the carrot, you'd eat the potatoes or the turnip. All the stuff above you never typically eat. They just get rotted in the field or burnt indiscriminately in some cases as well. So that waste is what we feed into our process. And then our process, as I said, separates it using heat in the absence of oxygen so that it won't combust into biochar and a vapor phase. So the biochar, we've done some great work in this project with Coal Products Limited, Cpl, and Andy's going to tell you a bit more about that later. And they specialize, of course, in that they have a massive market in the UK and Europe for producing and supplying smokeless fuels, which many of you are probably familiar with in Sainsbury's or Tesco's. And our process removes the smoke so that we can have a quality product that can do that. But apart from biochar, smokeless fuels, we can sequester biochar into agricultural soils as well to improve the nutrient and the moisture retention. Okay, so that's what we would typically look at as applications, and we investigated in the project as to what we can do with the solid phase of the pyrolysis process. The vapor phase, we can do some other interesting things with that. So of course, one of our main focuses is that we want to generate electricity and provide energy access to rural communities who have an abundance of agricultural waste, but no grid anywhere near site, and not one coming anytime soon either. So we can convert the vapors into electricity. We work with a manufacturing partner, hello Claudio, from Italy, EMEES, and EMEES UK as well. So, to give us a capability for generating electricity from the vapor phase, we can have an either-or scenario. So we can either be in power generation mode or heat generation mode. So we can give you 100 kilowatts of electricity, which is enough to power a small village of about 5,000 people in Africa. And alternatively, this can be used in agri-food processors. And they also like a lot of heat if they're an agri-food processor for, processing the crops into finished products. So we can produce about 700 kilowatts of thermal energy. And then the waste heat from that thermal energy can be used to drive an absorption chiller, which can give you cooling as well. So this is an either-or scenario between power or heat and cooling. And then alternatively, if you don't want that, but you want to actually produce commodities from your waste, because of the value and, what you want in return, maybe foreign exchange, then we can also produce bio-oil. And the bio-oil is a condensate from the vapor phase. And so we can upgrade that bio-oil condensate. And this is the work that we've been doing with Aston University in this project. And they've come up with some exciting stuff that Christiani is going to tell you about. Method for converting that bio-oil into a diesel blending component, but also more interestingly as well, kerosene. And this kerosene typically is used locally, for lighting and for cooking. But more interestingly, if we can go even further, it can be converted into jet fuel. So, that makes it a very valuable, high-value commodity from something that was previously just rotting in the fields for these off-grid communities. So it's not just about creating energy access, but it's also about now, providing a way for these communities to start adding value to their, primary production. And if I just skip back again to the power generation bit, one of the things that we wanted to test in this project, and this is where, working with Ethio Resource Group and Acceleron, was, what's the most efficient way of distributing the electricity that we produce when we want to reach these communities? And in Ethiopia, very different to, say, like somewhere like Nigeria, where populations can be very dense. In Ethiopia, they're more dispersed. So putting mini grids into dispersed communities, not very cost efficient. So all of these kind of things are what we were exploring in the project, and why we thought, this is a much needed piece of research that we needed to do in order to test our commercial model and also our technical model as well. Okay. So Lifecycle analysis was where, we worked with the University of Surrey. This has been a brilliant opportunity for us to really understand, put our technology into context, in a way that we can compare it to other technologies and, incumbents. Why is what we're doing so good? So University of Surrey have provided some great support to us, and they've also done some additional work, which going back to that slide on the bio-oil upgrading is really what June was going to tell you about, because there's certain components that we need as well that University of Surrey helped us had a much bigger, deeper look at. So really the key finding of the life cycle analysis, which I'll call LCA from now on, it suggests that there's an overall energy efficiency of our system, our pyrochemistry system, about 67% when it's integrated with bio-oil upgrading. So this is really exciting, because it shows us that, yes, there is a real, potentially, very valuable commercial model for creating commodities from waste. And then that, of course, makes the work that Aston's been doing very much more important as well. Recommendations that came out of the LCA was that we need to develop a sustainability protocol. And this protocol would really tackle 3 key things. Make sure that when we're using biomass, it avoids competition with local use. As I said, we don't want to be, taking away materials that other people are already using for something else. So avoiding competition, ensuring the sustainability of that feedstock, and then also, how we look at using batteries as a low environmental impact, for power distribution. Now, there was a lot of knowledge transfer from University of Surrey to our team, so that we've now developed additional capabilities in-house, thanks to the great work that was done. And that means we're able to now, using the data collection methodology, LCA data collection methodology, we've got a way that, in future we can do LCAs ourselves. And that will help us produce accurate and appropriate LCAs, looking at using the feedstock and the location data that we gather. Now, the other important thing that, as I mentioned earlier, and this is where June was going to talk a bit more, is about how we can look at integrating hydrogen production to our pyrochemic process. And that's really important when coming to upgrading the bio-oil. Okay, but you'll hear more about that later. So, geospatial analysis. We need to know where people are, and then we need to know how they're spread and distributed, and we need to know the proximity, of settlements, to major, production of biomass. So that's really what we used geospatial analysis to do.
Just to tell you, 2 minutes left, Simon.
Okay, so this is what happened, when I was mentioning about we could then, compare the settlement dispersion, which is a very different model to Nigeria. Okay, and then, of course, for the battery rental market, we needed to get an idea of how far, these batteries can travel, and, so therefore how effective it is as a distribution method for power distribution compared with a mini-grid model. So, and then of course, we wanted to know the size of the populations at those locations so that we could see, is it going to be commercially viable? If there's only 2,000 people, probably not. If there's 30,000 in a location that have electricity, probably a very good case. Right. The other thing that, of course, we wanted to take into account is about gender equality and social inclusion. Now, promoting, technical training and understanding how women engage with our model is very important, especially when it comes to looking at how we're going to recruit, because we're going to do a lot of local recruitment. And then that has to, we did some work that informed the recruitment process as well. Okay, social media, of course, was very important. We've had a lot of people, unfortunately, as Bernie said, because of bandwidth issues and other issues, there might not be so many people joining us from Africa, but through the social media posts, there's a lot of people, as you can see, that have actually viewed. There's been a lot of views of to make them aware of what we're doing. So in Ethiopia, the largest by far of our, African projects, 185,000. And then, of course, this gives you a look. So Facebook mostly, Instagram next. And then most of these viewings are taking place, the majority are in the 26 to 34 age group. And then, of course, the gender balance for Ethiopia wasn't as great as in West Africa, we found. So we still need to find out why that is. And then most of the viewings of social media postings were happening on mobile phones, but in Ethiopia, it looks like much larger percentage actually do access via PCs and laptops, which is more than West Africa. So here is, I'm not going to play this because I don't have time, but we've got a great video done by Catalina Maria, which is going to tell you all about carbon carbon removal versus carbon offsetting, which most people know about, but carbon removal is the only way to achieve net zero. You can't achieve net zero from carbon offsetting. So I recommend you to watch that. You can find the link on our website. And sorry, I'm trying to make sure. Okay. And this is really as part of a sustainable learning in 5 minutes social media post that really just educates people to tell them, important things about our technology, because our technology is a carbon removal technology. And as you can see here with carbon offsetting, you still end up with carbon going into the atmosphere. To achieve net zero, which is over here, you need to remove carbon from the atmosphere. And that's exactly what Pyrochemic does. So this is why this technology is a very timely technology. This has been a really timely project, great partners. We've learned a lot through the process. I'm really excited for the future, and I'm sure you're going to learn a lot by listening to all our partners that are coming next. I just want to thank all of our partners who've been involved. It's been a pleasure and a privilege and a great experience working with you all. Thank you very much.
That was great. Thank you very much for that, Simon. So the next up to speak is going to be Andrew Gill from Cpl Industries. Andy, over to you now to talk about what you've been doing with the biochar.
Okay, 1 second. Everyone, well, can you see that, Bernie, just to make sure?
Yes.
You can?
Yeah,
Right,
that's perfect.
Hi, everyone. So I'm Andy Gill. I'm the R&D manager for Cpl Industries. As Simon alluded to, we actually are the largest smokeless solid fuel supplier in Europe. Many of you might have seen our products in Sainsbury's, Tesco, Asda, etc. As you can see there, one of our products, which was actually over 50% renewable material, because we use molasses as a binder. So it's probably actually around 55%. What we've been doing on this project is, while sometimes it's been a bit challenging getting biomass directly from Africa for numerous reasons, COVID probably being the biggest issue, we have been taking a lot of different biomasses from Europe and around the world that we can get hold of, and undergoing quite a lot of extensive testing. So what we do when the biomass arrives on site, the first 2 pieces of analysis we do is approximate analysis, followed by a calorific value test. And this is of the raw biomass before charring. We, as you can see there's just a select few that we've tested. I think our database probably covers around 150 to 200 different biomasses. So you can see how much kind of research has gone onto this, and also before the project even started. So we've been taking some of these materials, we've been then charring them on our pyrolysis rotary kiln, and then using those to produce some briquettes. Nothing's ruled out at this preliminary stage unless the ash is really high, because obviously if you're starting with a biomass with ash over 20, by the time you've charred that ash as a percentage is going to go, well, it can over double. You don't want to have a fuel product that's just going to leave loads of ash behind. Also reduces the calorific value. So part of the project has also been looking into new renewable binders. So what we've done here is, you can see we haven't labeled them for IP issues, but we've also been taking new additives to existing binders that are well known, cover molasses, starch, and some resins. And we've been searching all over the place for some renewable additives that can increase the strength. And that's the crush strength of the actual briquette itself, which I'll discuss a bit further later on. So we've also been working with external partners outside the project, and they've been helping us to do some pilot scale testing. But the graph you can see on the screen right now shows you the TGA profile of the binders, and that's not just individual binders, that's mixes as well. So you have the temperature on the right, and then the duration of the testing, and then the percentage mass loss on the left. We've heated these all the way up to 1,000 degrees. And one of the reasons for that is, in an industrial market, so they want the briquette to remain as a briquette right up until around 1,000 degrees for their specific application. We've also been taking a lot of time procuring these binders and additives, and that has actually taken up a significant amount of the project time. So if we go to the lab scale testing, this is the hand press trials. Here you can see some examples of what we've done. So we've taken 50% biomass, in this case you can see olive, pistachio and macadamia, and mixed it with a 50% R&D blend, which is different types of coals. This can be petcoke, anthracite, and a specific additive in this case as well. You can see how the additive has increased all the biomass's crush strengths in the briquettes, a good about 20 to 30% on the olive and pistachio, a little bit less on the macadamia, but it still shows an improvement. The control will be, it's just molasses. So the control also is not biomass, there's no biomass in that, it's all coal. And the trouble with biomass is when you're forming a briquette, it's much more difficult to form the briquette compared to when you're just using coal. So that's why we've been searching high and low for other binders that can increase the strength of all the different shapes and sizes of briquettes we actually make. So once we've done the hand press trials, we then move on to a pilot scale rolls press machine. So, which is, I'll just move on to the next slide actually. I'll go back to the Pyrogenesis binder, but on this one we use a large rolls press which can take between 50 and 100 kilograms of material, whereas the hand press uses around 1 kilogram material, so it's quite a big upscale. The table you can see here covers a range of testing. So the shatter testing is where once the briquettes are formed, they're dropped from a height of 2 meters, and then we measure as a percentage of the whole briquettes that remain. Then we do a crush test on the dry and also a wet crush test. We're aiming really the higher number the better, because if you're transporting this material all around, well, Europe and across the sea, then it's going to have a lot of weight on it, and you don't want to end up with just dust at the end. So you can see how not only the crush strength but the waterproofness as well. We've not included this in the slide, but that's also another important factor when we do our analysis. So Pyrogenesis actually provided us with a binder from Africa, and you can see the results there. There's one that's got in this column here, it's nil. That's because we are going to repeat that. What happened is we actually had some other material that caught fire in the oven and destroyed these briquettes, but we will be finishing this as well. So all what's happened, this binder was mixed with water, and you can see, unfortunately, in this case, the crush strengths were a lot lower, considerably lower than the molasses control. But we are still trying to find ways to improve that, and we could try different ratios of binder mixed in with this binder provided by Pyrogenesis. So once the briquettes are produced, the final test we normally go through before emissions testing is the fire tests. So we load the fire as by the ASTM standard. We load the fire 3 times, and here we're looking for peak temperature or heat output, and also duration of the fire. So ideally, you are wanting a very high temperature, but you want the fuel to last. You don't want to have to be reloading the fire every 10 minutes, for example. So we normally compare our new product development against existing products that are in the market, whether that's our own or whether that's competitors. We're also looking here to see what we call it the SJ number, which is how much ash is remaining on top of the grate of the fire. That's also very important, because the way the customer sees it, they don't want to see just a pile of ash and some unburnt carbon left on the grate, which is then a waste. So we look for a very low SJ number during the fires. And I think that covers the CPL work. So if there's any questions.
Okay, great. Thanks for that, Andy. If there's any questions, we'll probably take them at the end.
Okay.
It's probably better, but that was great. Thank you very much. So moving on, our next speaker is going to be Dr. Christiani Scalda Ferry from Aston University, talking about the work that they've done with the liquid component of what the machine is producing. So over to you, Christiani.
Thank you. Is everyone able to hear me?
Yes.
Let me share my screen. Can you see my screen? My
Yeah.
presentation? Oh, thank you. Good afternoon, everyone. My name is Christiani. I'm a research fellow at Aston University, work with Dr. Jude at the EBRI Energy and Bioproducts Research Institute. And in this webinar, I will give a brief explanation and a brief talk about the project that we are developing here at Aston in partnership with Pyrogenesis, entitled as Production of Biokerosene Fuel Blend via Catalytic Upgrading of Pyrolysis Oil. In this presentation, I will give an overview of pyrolysis and present some properties of the bio-oil, which is produced from the pyrolysis process, explain why these properties imply some limitations in the usage of pyrolysis oil as a fuel, follow with a couple of examples about the strategies for pyrolysis oil upgrading, and subsequently, I will talk about the concept of this work and showing some of the results that we've got so far. So let's get started with a brief introduction about pyrolysis of biomass. So in the last years, the biofuels play an important role to mitigating climate change from the development of sustainable process that can be replace the use of fossil fuels. And pyrolysis is a promising technology that converts biomass, for example, wood, straw, and agricultural residues in energy vectors, such as biochar, bio-oil, and syngas. And in this diagram, as Simon also mentioned before, the pyrolysis process is based on the heat, the biomass, for example, wood, in the absence of oxygen, usually in nitrogen atmosphere. And as a product, we can get a solid product that we call biochar, a liquid product as we call bio-oil or pyrolysis oil, and also a syngas or gas products. So the main focus in this presentation will be the bio-oil, and depending on the configuration and the conditions of this pyrolysis process, the pyrolysis can be classified as fast pyrolysis, intermediate pyrolysis, slow pyrolysis, as well as gasification process. The fast pyrolysis is performed at temperatures at around 500 degrees Celsius in short residence time. And the main product in this configuration process of pyrolysis is a liquid, around 75% of liquid in one phase. So in contrast, the intermediate pyrolysis process, which is carried out around at temperatures around 500 degrees Celsius as well, but longer residence times, results in two phases of liquid products, an aqueous phase and also our organic phase that we call bio-oil. So for other configurations, such as slow pyrolysis, it's possible to produce high yields of char, as for example, in the slow pyrolysis in the mode of torrefication process, or a slow pyrolysis where we promote decarbonization. It's possible to have like a very balanced yields of liquid, solid, and gas. So in the gasification process, the main product is the gas. So from this table one, clearly, the best option to produce bio-oil is the fast pyrolysis process, which we have like a yield of bio-oil around 60% and 75%, with up to 20% of water in one only phase, and less char formation and less gas formation as well. So the bio-oil is a dark and quite viscous liquid, as you can see in the left of this slide, in the picture on this slide. And the bio-oil is composed mainly by oxygenated compounds, such as acids, phenolic compounds, carboxylic acids, ketones, aldehydes. And these oxygenated compounds imply in several properties that makes the bio-oil present a poor combustion performance. For example, the bio-oil presents a high viscosity, and the presence of carboxylic acids, for example, imply in a bio-oil with high acidity and corrosiveness as well. Due to the high presence of oxygenated content, the bio-oil presents a low heating value when we compare with gasoline, for example. And also bio-oil shows a low volatility and a low thermal stability, which makes the bio-oil tends to polymerize during long periods of storage. Furthermore, bio-oil is immiscible with fossil fuels, and because all of these characteristics and properties, the bio-oil shows a poor combustion performance. And that's why upgrading process is needed before it can be used as a biofuel with suitable combustion properties. So in terms of upgrading strategies to improve these bio-oil characteristics and properties, usually we have like physical and chemical methods to improve this bio-oil composition. And in this slide, I show a few examples of chemical strategies to upgrade bio-oil, such as process based on esterification, cracking process, hydrogenation, and hydrodeoxygenation process. In summary, all of these chemical process aimed to modify the chemical composition of the pyrolysis oil to improve your fuel properties, make it more suitable for the end use equipment such as engine and also turbines. So now move on to some of our results. In this slide, I show some of the characteristics and properties of the pyrolysis oil from Aston, which was produced from fast pyrolysis of pine wood. And as you can see in the table 2, this bio-oil has a high oxygen content, around 50%, which means that if you want to have like a liquid biofuel composed mainly of hydrocarbons, carbon and hydrogen, the maximum yield will be 50%. So as you can see, this bio-oil presents a low heating value, around 21 megajoules per kilo, and also a low water content. The low water content is quite important because the water can deactivate the catalyst during the upgrading process, and also decrease the yields of the biofuel yield. So as you can see, the properties of this bio-oil implies in several characteristics that promote that in this case the bio-oil has like a poor combustion performance, and that's why we need to upgrade this bio-oil. And here in this next slide, I show that like the Aston rule in this
2 more minutes, please, Christiani.
Yeah, in this project was developed a 2-stage catalytic upgrading process for biokerosene production. So this catalytic processing is based on 2 steps. A first step of stabilization of bio-oil at low temperature in hydrogen atmosphere, and a second step of hydrodeoxygenation. In this picture, in the bottom of the slide, you can see the evolution of this product after the first step and after the second step, where we have like a light yellow biofuel with low content of oxygen. So lastly, I show the results of this pyrolysis oil upgrading, comparing the bio-oil, the bio-oil plus solvent before the upgrading, the upgraded blended fuel, as we call biokerosene, and the commercial kerosene as a standard parameter. So from this table 3, we can see that like the bio-oil had like 50% of oxygen content, and after this upgrading process, the oxygen content decreased by 99%, which means we have like a biofuel composed mainly of hydrocarbons, carbon and hydrogen. So as a consequence of this oxygen content decrease, the hydrogen content increased by 31%, and the carbon content increased by around 25%. So In this process, we've got 20% of upgraded bio yield, which is a good result because consider that we have like 50% of oxygen and the maximum yield that we could get is 50%. 25% of upgraded biofuel yield is it's a really good result. And if you compare the rating value of the commercial kerosene or biokerosene, the upgraded blended fuel, they are very similar results, basically 46 megajoules per kilo, which means this upgraded biofuel, blended fuel, has good combustion characteristics. So, and that's it. Thank you very much for your attention and for all partners, Pyrogenesis and the Innovate UK, and also EBRI. Thank you very much. If you have any question, please feel free to ask and then of this webinar or type in the chat.
Super. Thank you very much for that, Christiani. That was great. So yes, if anybody has any questions, we already have a few that have come in. Please keep your questions coming in, and we'll ask those during the Q&A session at the end.
Yeah, brilliant.
Great.
Okay, thank you, everyone. Good afternoon. This is Hilawi from Ethio Resource Group, Ethiopia. Our company is engaged in the field of energy and environment. Mainly, it does consulting service, but recently we moved into energy enterprise, mini grid development, and the basic services that we provide, advice to government, policy advice, and we also conduct trainings on energy efficiency and renewable energy, resource development and implementation, and we do things related to that as well. In addition to that, we also do installation of systems and monitoring of renewable energy projects on the ground. It varies from solar, wind, microhydro, and biomass, from the very basic thermal cookstoves to mini grids. In 2015, we just got into mini grid development. So we developed the first private sector-owned mini grid in Ethiopia. So sometimes we boast of getting the first 2 licenses, 001 and 002 for mini grid. But that was a very learning project for everyone, for us as a developer and for the regulators, as a regulator. There were so many glitches in the regulation, so that really helped go through the different processes. So we consider ourselves in the mini grid sector as pipe cleaners. So we've actually heard about the pyrolysis technology. We heard the science of it, and also the technology that was developed by Pyrogenesis and Aston University. Well, we've also actually learned that if it is wisely used, it is the most sustainable resource that can actually provide wider access to clean energy. So to bring all this into context, or the relevance of the technology and the resource, I just want to take you through the reality on the ground. So the case study we took was Ethiopia, and what is there that we have. Ethiopia is a population of 110 million, and 80% of it is rural. Electricity connectivity is very, very low. The connection rate, about 30%. This is connected to the grid. So the off-grid, or those that are not connected, use inferior quality electricity, like solar lanterns or solar home systems. Inferior quality in a sense that they don't get wider access. But the majority of it, like 43% of the population, they don't have any electricity access. So this has very relevance in terms of providing access to the unserved population of Ethiopia. And not only Ethiopia, but in most third world countries in Africa and Asia, maybe perhaps in Latin America, South America, this technology has a wide application of it. So now, we might question why biomass, how about solar, how about wind? Let's see, let's have the perspective and the spectrum of the energy use pattern in Ethiopia. In this slide, what I really want to put there is the resources that we have. Yes, we do have the hydropower resource. In fact, our grid electricity, over 95% of it now with the new additional hydropower plants, nearly 99% of the power would come from hydro. Solar irradiance, we are, closer to the equator, and we sometimes boast of having 13 months of sunshine, and the 13th month is only 5 days though. So the average irradiance level is 5.5 kilowatt hour per meter squared, and we also have good wind resource. But when you see the biomass resource, particularly within agricultural waste, we do have really quite abundant resources, though we are not using them very efficiently. It's only less than half of that we have currently used, and those that we are using them, using the traditional conversion technologies like cook stoves and things with the efficiency of which is very, very low. So the half circle that you see basically shows you the energy consumption by fuel type. So you can see that the biomass by far is greater than any of the other fuels that you see, being consumed by the population. So what I really want to bring to your attention at this moment is when we think of pyrolysis and biofuels and using them for heat and power, then we are already using biomass. So it's a matter of using them very efficiently and for high-grade energy. So this is something, the resource is something that we are already using. So the pyrolysis technology would actually help us use it for power and heat at a higher values. So when see the case study, this is the area that we have our mini grids. Basically, our mini grids are powered by wind and solar hybrid, and it's battery based as well. So this is the area is called, is located in the central highlands of Ethiopia. It's called EMEES. This is a kind of zone, and the population is about 145,000. But one kabale, the zone is divided into 22 kabales, and nearly 90% rural. So our mini grids are located in 2 kabales, and particularly addressing only villages in the kabale. Kabale is the lowest government structure in Ethiopia. So the connection rate, all in all, in the zone is less than 10%. So when you go to the rural areas, it is much, much less. In fact, it's less than 5%. Or in some areas, for example, the village that we electrified, they don't have any connection at all, except that few of the households already adopted solar lanterns, and so very few of them solar home systems. The main occupation in these areas is agriculture, and then they also have some livestock. So this is a little bit of a background of the villages that we do have in mind when we think of mini grid and extension of mini grid services and providing energy access. You can see the kind of villages that we have there. And the picture at the bottom is the distribution line for our mini grid. So currently, because as Simon initially stated, unlike Nigeria, we do have clustered but scattered households. So we have 6 mini grids, microgrids, I would rather say, but the intention is as the demand grows, we'll connect at least 4 of them together, and because they are close to each other. But at this moment, connecting them it's rather not economically viable. But when the demand increases, then that's the plan that we have. Through our mini grids, we've already connected from 250 to 300 households, and they are actually enjoying the better lighting service and mobile phone charging. But for productive use to come, a number of things need to work together. But there are already a few things on the ground. There is one diesel engine powered grain mill, and also government-owned generator that drives the water pump, which is not currently functional. So we are trying to extend our services, to this systems, but technology is also one thing that we are, particularly when it comes to the grain mill, the technology that is appropriate for mini grids. The running mini grids on a private basis, private company.
Just one more minute, please, Hilawi.
Okay. It's not really easy. So the battery charging service is additional source of revenue for the mini grid. And second, it also increases the service that extends the service that the mini grids would provide to the unserved, unconnected communities. So more households would be reached, and also improves the revenue of the mini grid, increasing its viability. So for this, we got the lithium iron phosphate batteries from Aceleron. So basically we are testing this, and the picture that you see, if you see it on column wise, the first column is the battery. We put a bag so that it would be easier for transportation and handling, and the battery charging unit, and people taking the batteries to and from the house to the charging bay. And the last one is the households lit with the batteries. They enjoyed it. They love the light, the clean light, and also it's clean in the house, rather than burning kerosene or firewood for lighting. So this is then you'll hear it from the Lifecycle analysis perspective from Mari later. Basically, this is the kind of background that the whole purpose of the technology and the resource that we are aiming to extend in Ethiopia and other similar countries. Thank you. If you do have any questions, then I'll be happy to respond later.
Great. Thank you very much for that, Hilawi. That was fascinating to see how the situation in Ethiopia is on the ground is actually mirroring what the other partners are trying to do over here. So moving on to Dr. Laura Aston from Aceleron to talk a little bit about the battery technologies that you've been developing there. And then at the end of the webinar, we'll go back to Dr. Mari to talk about the work that Surrey have been doing on lifecycle analysis.
Hi all, thanks Bernie for that introduction. Nice to see everyone. So I'm Laura Aston from Aceleron, as Bernie just said, and hopefully you can see my screen.
We can.
Thanks, Bernie. So I'm just hopefully going to tell you today a little bit about what Aceleron do as a company and how we're helping in this project. So our overall ethos as a company is creating batteries for life. So imagine you're driving down a road and something goes wrong with your vehicle. You wouldn't scrap the vehicle, you would get it repaired, right? So why don't we do this with lithium batteries? Batteries are made up of hundreds of subcomponents, and typically it's just one or two of these that would have gone bad at the end of the battery's life. But because of how they are designed, we have to throw the entire thing away, which generates a lot of unnecessary waste of valuable assets, which obviously has a terrible environmental impact. And just to give you an idea on some of the numbers around this, so by 2040, from electric vehicles alone, not considering all the other batteries that are obviously going to be all over the world by this point, there is an expected 22 million meters cubed per year from electric vehicle batteries of waste. And just to help you visualize that a little bit, there's a nice little infographic here. But that waste per year would fill the Melbourne cricket ground 14 times. So as you can see, this is really something we need to get a handle on now and ensure that we're doing something about this before it gets to be too much of a problem. So this is where Acceleron comes in. So we have designed our batteries different to typical lithium batteries. So in the usual method of putting these batteries together, all the parts are welded together using glues and welds as well. And it makes it impossible to service, really. So that's the need for throwing the entire thing away. So our design uses a compression technology, which allows us to, if there is an issue with any of the parts inside, after however many years, we can open it up using our predictive maintenance and also testing of batteries afterwards as well. We can figure out which parts have something wrong, replace them, and then put that battery back out onto the field. So I would just like to tell you a few things about the different areas we currently work in. So some of the partners we've worked with still and previously are down the bottom of the screen there. And really they all see the value in the serviceability and maintenance of the batteries, which is going to allow us to reduce that waste from the future. So we work right up from home energy storage in places like the UK and the Caribbean. This year we're bringing out a large rack-mounted energy storage, which will allow us to facilitate commercial storage. And then we also go right down to much smaller devices, which is what I'll tell you about in a moment, which just allow the combination of solar to be used in quite a lot of African homes that could potentially be used for lighting or TV. So predominantly we work in Kenya and we have a facility there, and we're looking to expand into other countries, which this project has helped us do as well. So what we do in Kenya specifically is we work at the waste centre there, where we are able to collect and sort battery cells that have come from other technologies, which have those non-serviceable packs. And if it wasn't for our technology and what we're able to do there, these would all just go to recycling instead. So we're able to take the Kenyan waste from across the country and repurpose it into batteries. So what we do to allow us to do this is we disassemble the batteries. We then test the cells quite vigorously to ensure that they are safe to be reused. And then those cells are sorted, and using algorithms, we understand how those batteries can be best placed together into a battery pack to enable them to be put into use. And so it's these batteries that we've been using and providing Halawi in Ethiopia to assess how we can expand his mini grid availability to more rural customers. So I'll just say a very quick word about the differences between specifically our lithium batteries, but against lead acid, because typically in mini grids and in quite a lot of other applications, lead acid is sort of the incumbent technology. So the way we have produced our lithium batteries is that they are should be a similar voltage and capacity so that they can be used in similar scenarios. However, there are some great benefits to them. So if you can just see here, hopefully, that you're able to go to a much higher depth of discharge with lithium batteries. And also the lifetime is drastically extended as well. So even though with lead acid you're only going to a low depth of discharge, still the failure rate after 2 years can be quite high. So another really good benefit is the weight of the batteries can be up to a third lighter for lithium. So as you can imagine, if customers are coming to one of Halawi's charging spots, it'd be quite difficult for them to be carrying something that's sort of 50 kilograms back to their home. So this 15 kilogram battery is much more acceptable for them to be doing that with. And then additionally, with the weight difference, there is also the size difference. And so that the smaller size will also make it easier for them as well. So just hopefully highlighting there that the lithium battery certainly makes sense in this situation to be using to extend the mini grids. One thing I will just say here, though, the downside of lithium compared to lead acid is it is nowhere near as recyclable. So that's why the benefit of using the second life batteries is so high here. And additionally, the lithium batteries are typically more expensive. But again, because we're able to use second life, then that really brings the cost down as well. So just as a further detail of particularly what we've done in this project, we provided Hilawi with the 2 batteries types that you can see at the top of the screen there. So one of them is a 12 volt 19 amp hour battery, which is sort of, sorry to be gesturing here, but quite small. And that's sort of about 5 kilograms. And that has been shown to be able to run lights in customers' homes for up to 5 days before they then need to bring it back to the charging place for a recharge. And then we also have the larger battery, which is the 12 volt 100 amp hour. And as you can see there, it's quite a lot larger. And that's the 15 kilogram battery. And it just had 2 handles at the side, so it wasn't the easiest thing to carry, which is why Hilawi needed to use the leather packs to enable his customers to take them home easier. So we had some really good results with those. Those larger batteries were able to run lighting and other appliances in the home for weeks at a time. And he also did the lead acid comparison at the same time as this, and he found that those lead acid batteries were needing to come back after sort of 2 and 3 days. So really positive learnings from that. So then what we have also done during the project, unfortunately, we weren't able to deliver these to Hilawi for testing, but we have redesigned our the battery pack. So this is the battery that you can see, say, an eco store down the side. And this is the same battery as the top right of the 12 volt 100 amp hour essential. And what we've been able to do here is use human-centered design to really understand, how people are going to be using these batteries. And the addition of the handle just means that the carry case would not be necessary, and it's just much more comfortable to sit in your hand. The weight has all been positioned within the battery so that it is quite nice to carry that way. I'm hopeful that the design may have reminded some of you of a jerry can. And so from speaking with Hilawi, he suggested that quite a lot of his customers would be really used to carrying things like jerry cans to and from their homes for things like petrol or even other goods as well once they've been cleaned out. So hopefully it would have quite a high acceptability rate for his customers as well. And then finally, this product has been, as it's sort of a new design, it has been made more robust, and it does have an even better capacity than previously, but within the same weight and size dimensions. So we've hopefully been able to achieve quite a bit in this project, and I'm hopefully going to be working with Hilawi and the rest of the team in the future as well. So thank you very much for your time. I will stop presenting now.
That's great. Thank you very much for that, Laura. So finally, we're going to go back to the presentation from the University of Surrey and Dr. Mary. Mary, are you going to try presenting it yourself, or are we going to go with...
I'm going to share my screen, Bernie.
You're going to share your screen, right.
I think it's going to be easier just to try and do it this way.
Yeah.
Hold on a second.
Sorry about the failed attempt last time. I'm not sure quite what happened there, but the system doesn't seem to like the PowerPoint presentation that I have, but we'll take it from Hilawi's computer, from Simon's computer screen.
Okay, is that working now? Can everybody see that?
Yes, we can.
That's great, thanks.
Okay.
So, as I mentioned, this is work that's been carried out at the University of Surrey in support of the Pyrogenesis project, the EMEES project, by myself and Professor Juma Sadikan at the Centre for Environment and Sustainability. Next slide, please. Thanks. So, as I was saying, we have all heard in the last couple of days more than ever how the climate emergency is affecting the globe. And for a number of years now, biomass for bioenergies have been promoted as a means of reducing greenhouse gas emissions, reducing dependency on fossil fuel, but also to add value to agriculture and horticulture and forestry systems. But I'm sure many of you are aware of the controversies associated with that, including competition for land, emissions associated with land conversion, loss of biodiversity, the impacts on local communities, and also particularly in countries such as Africa, the issues associated with food access and affordability. And these are just, I'm sure, a few of the issues associated with biomass use. However, the EU and UK, and certainly the US as well, have developed mechanisms to report on bioenergies which have been promoted by specific renewable energy policies. And these have been based around lifecycle assessment methodology for environmental impacts and sustainability methodologies for social and economic impacts. Next slide, please. Sorry. Yeah, here we go. However, in contrast to the situation in the Europe and perhaps North America, in sub-Saharan Africa, as we've heard from Malawi and as we've seen in some of our field trips, in some areas of Ethiopia, particularly rural communities, biomass is actually the only source of energy that people have to use for cooking, heating and lighting. And there's different issues associated with the biomass use there, where air pollution and health are bad problems, obviously, because the smoke from the fires inside enclosed spaces can cause respiratory problems. The biomass will all be sourced from a local area, so there's depletion of local biomass and forest resources. Some of the biomass that's used is, for example, manure from animals, which means that that's not necessarily going back onto the land. And there's also a number of issues associated with the collection of biomass, not least that it's labour intensive, but also security for women, who are often the people who have to gather the fuel for fires and energy use. The other interesting component of this is that agro-industry development is a key part in many of the development agendas for many sub-Saharan African countries. The management and valorization of agro-residues and waste can provide new opportunities for developing energy access and improving the profile of bioenergy use, and also improving waste management and returning nutrients to soils. Next slide, please. Simon?
Can you hear me?
Yeah.
Okay, I've shared it at my end. It says the EMEES proposal, yeah? And it shows, is it not?
Okay, thank you.
Okay.
So we've heard quite a lot about the EMEES proposal already, but just as a recap, it's a bioconversion technology which will provide 3 potential energy outcomes. And as part of the proposal, we've also looked at the mini-grid extension service offered by the Acceleron technology for repurposed batteries. Some of this work in relating to the biomass availability is related to a previous project which Ethio Resources and University of Surrey were involved in, a project called AgriSen, which looked at how the agricultural industry can be in some ways a sort of central point for energy provision. And as part of that, agro-processing residues and wastes were considered. So biomass from field and processing residues, for example, the pictures here are sesame seed. And unfortunately, the pictures have got a little bit out of focus because we're using another way of presenting them. But the seeds there are actually sesame seeds, which are tiny, tiny, tiny. But you can see that the waste that's produced as a result of sesame growing is quite considerable. And this actually becomes an issue for management after the crop has been dried, because it's difficult to break down if you just put it back into the soil. So things like sesame, maize, coffee husk, these are all processing residues which were considered in a lot more detail as a potential biomass resource from Ethiopia. The EMEES project also recognises the need to address the sustainability of biomass supplies, and the three pillars of sustainability, as we know, are the environmental, social and economic impacts. Next slide, please.
Changed it. Hopefully it'll come up sooner rather than later.
So we basically started to develop a framework using life cycle assessment as a tool for environmental LCA, assessing environmental impacts. And then we took a look at the United Nations SDGs, the Sustainable Development Goals, and we did quite a comprehensive benchmark of the SDGs. And then using a techno-economic tool which was developed at the University of Surrey, we've provided a framework which will allow different impacts to be considered if we look at different energy outcomes, as well as the actual pyrogenesis process itself. So yeah, as I've said, we looked at the potential biomass feedstocks from a sustainability perspective, the actual pyrogenesis process, the three energy outcomes, and then the Sustainable Development Goals as a benchmark. And then we focused on coffee husk because it was, we could only, in the time that we had, look at one biomass. The pictures on the right here show that the coffee processing system in Ethiopia is still quite manually based. There's a need for energy to assist with the milling of coffee husks. Coffee husks themselves are quite friable. They're quite suited to the pyrogenesis process, but based on their chemical characteristics. But depending on where you are, the coffee husk can either be a complete waste. So there's the picture on the top right there. This is literally mounds of coffee husk which are dumped, and then you can see there's a spontaneous combustion going on there. It just happens. They go alight, creating their own environmental issues. Conversely, closer to more urban situations, so the picture on the bottom right is close to Addis Ababa. The coffee husk is actually used as a commodity, or small-scale commodity, where people will buy the husk in order to fuel their fires or their fireplaces for cooking. Next slide, please. We've heard from Malawi as well about actually how much is available as well in terms of the whole of the sort of Ethiopian area. So a lot of the next stages of the work that the pyrogenesis company will be looking at is where will be the most suitable locations for their facilities.
Has the benchmarking of sustainable development goals slide come up yet for
Yes.
you? There seems to be a slight delay. Sorry about that.
Yeah. So I'm sure that many of you are familiar with the Sustainable Development Goals and what sustainability means. We've been talking about it for a long time now. So what we did was, based on the 17 SDGs, we worked on a methodology which was developed by a team at UCL, which looks at the benchmarking SDG 7, particularly the energy SDG, against the 16 other Sustainable Development Goals. And in this case, it was considering energy systems in a generic sense. So what we did was we took the SDGs and we did a second and third level benchmark. So the second level was where we considered how pyrogenesis systems, if they were deployed in Ethiopia in a more focused sense, in the sense that we were looking at Ethiopia specifically, and we asked the question, how would the pyrogenesis system impact on those SDGs if it was considering the feedstock inputs, that it's a waste management system, and that we're looking at 3 specific energy outcomes. We also took a look at the role that the Acceleron batteries might play in as being a separate waste management system. And at the third level, which would be future activities which pyrogenesis would do, where we benchmark the pyrogenesis system considering local level. And in this way, we're able to identify indicators of the SDGs which could actually be quantifiable. And you would consider those at some future locations or sites of the pyrogenesis facilities. Next slide, please.
Put up the life cycle assessment framework.
Yeah. So for the life cycle assessment framework, and I'm sure many of you are aware of life cycle assessment as a tool, it's a well-developed environmental management tool, which allows us to quantify over the whole life cycle of a product or a system, the environmental impacts associated with that product or system. And you can look at components of the LCA. So you can look at, cradle to grave or cradle to gate. So for example, we might consider feedstock production to the pyrogenesis plants, and then the end uses of the energies that come out of there. And the diagram on the left indicates those different systems, boundaries, and subsystems. So we followed the standard ISO 1440-1444 protocol for LCA development. We considered that coffee husk was a waste, so we didn't include any impacts associated with feedstock production in terms of allocating inputs to the production of coffee. However, depending on the location of the pyrogenesis facility, there would be a need to definitely quantify that biomass is a waste, and that would depend on the location of the facility. So where the coffee husk may be used for other uses locally, we would have to consider was there cost associated, or to make sure that that's not pulling away what was previously a free resource from communities that perhaps really need it. In this LCA, considering the three energy outputs, we would also consider what are the local requirements, and the pyrogenesis process could be fine-tuned to produce more energy or more solid or more liquid bioenergy as required. The biochar opportunity could also be for, as Simon had mentioned, going back into lands, and this is also as a carbon removal technology, but further information would be required at the local level about how that would fit into an agricultural system. And again, depending on what the actual location is, to make comparisons with other energy systems, we would have to look at what other energy systems might be available locally. Next slide, please.
If we could just have the last minute or so, Mary.
Okay. So Juma Sadukan, who's at University of Surrey, has developed a techno-economic analysis tool, which is based on pyrolysis kinetic modeling. It's based on integrated flowsheet simulations from Aston Plus, and you can find the actual tool in the webpage shown here. At the moment, it's been set up to consider the kerosene used for biojet fuel, but what we would intend to use it for is to look at the local conditions for the pyrogenesis facilities. So considering things like feed input costs, process parameters, and the desired energy outcomes. Sorry, Simon, this is the last slide. Next slide, please. Okay. So as we've mentioned, as you already know from the presentations before, there's the three-way energy system that the pyrogenesis process allows for. So optimization of bio-oil, biochar, or hydrogen production systems. Sorry, Juma's tool can look at hydrogen production as being part of the pyrogenesis process, or can look at it as being something that would be external, would have to be added into the process to take account of the processing characterization for the bio-oil conditions. So the model looks at in situ and ex situ hydrogen supply options. It looks at the three energy outcomes, and it allows the project to look at maximizing specific outputs. Based on current inputs and looking at kerosene as a biojet fuel, the model currently predicts that the bio-oil and biochar would come out at 14 to 16 pence per kilogram. But obviously, all of that needs to be translated into the local situation to make this applicable to Ethiopia. And what will be interesting also will be to consider the added-on component of the grid extension that we're looking at with the use of the repurposed batteries. This tool can be found at the website here and is going to be very useful, I'm sure, in the future, and can be applied to different sites. So that is my last slide. My apologies for the technical issues. Given that we practiced this a couple of times, I'm really not quite sure what happened, but can I just say it's not my technical incompetency?
Thanks, Mary. Yes, I think it was the webinar system
I won't be using it again myself.
Thank you very much for that. So that was our final presentation. So I'd like to thank all of the presenters for their presentations there. And if everybody can unmute themselves, we'll move onto the Q&A section. Obviously, we're quite close to the intended finishing time of the webinar. We'll overrun by a couple of minutes. That's not a problem. But we probably won't have the chance to cover all of the questions here. So some of them we can send the answers to by email afterwards. But moving to some of the most interesting general questions, there was one here about how this whole system, technical ecosystem that we've been discussing, could lend itself to practical opportunities for clean cooking. So what do our presenters feel about that? Is it just the electricity that can be used for clean cooking? How could that be done with batteries? What about the solid fuel component? The solid fuel briquettes that we're getting from that, are those cleaner than normal charcoal would be? Or what's the possibility of using the liquid fraction that comes out and the bio oil? Would that be clean burning? So what can be done about clean cooking, or indeed just the direct heat from the machine itself? Probably best starting that with Simon.
All of the above, Bernie. So, I mean, we did a project called Rural Industrialization via Energy Technologies in Nigeria, RIVET for short, as an abbreviation. And, that did look at using the heat to drive what was a gari frying process. So gari is a staple in Nigeria. So, and you have kind of like clusters of, anywhere between, tens to hundreds. And I think the biggest cluster we came across was about 1,000 gari fryers in one location. So to have a high concentration of people all frying gari in one location, it would make sense to plonk one of our machines there. And I see as well one of our project partners, Dr. Bola Asiru from the Federal Institute of Industrial Research, Oshodi, FIRO, is actually on the call. Hi, Bola. And Bola's team did a great job of working with our other project partners using human-centered design again to come up with a new gari frying system that would use the process heat that we produced, and therefore that would displace firewood, which is consumed in vast quantities for those clusters. I'll let other partners speak about how their technologies, especially like the kerosene and the biochar as well, can be used.
Christiani, maybe over to you. How clean is the what we produce with the bio oil? Christiani, are you there?
Are you able to hear me?
Yes.
All right. Yes. So at the moment, we're performing some characterization of this upgraded biofuel, and so far we needed to do the engine test, but we had done like some burning tests, and all the flame and all like the combustion test so far gave us like similar results when we compare with kerosene. It's a clean, a clean smoke when you burn this biokerosene. And yeah, but at the moment we are just finished this whole characterization to make sure that the biokerosene will have the same specification for the kerosene, the commercial kerosene. Sure,
thank you. And Andy, are the briquettes that we get out of this, can we be confident that those are cleaner than the regular charcoal burning?
I think they'll be clean enough definitely to produce energy, but also if you wanted to use them as barbecue fuel, I know that's one of our products that we would probably turn these biochars into, depending on the volatile left on the charring after the pyrolysis stage. Again, you'd want to produce a barbecue fuel that's clean. You obviously want a certain amount of volatile on there that allows for a easy lighting, but also a duration that the fuel would remain hot to obviously cook your food.
Great, thank you for that. So moving on to the questions, we've heard a lot about different sorts of biomass. I mean, can the machine and for the quality of the output materials, can it handle any sort of crop waste or biomass, or are there optimum ones that you would want it to use?
Right. So with pyrolysis, less moisture is better, less ash is better. So those are, and higher heating value is better. So these are some of the key criteria that Christiani, explained earlier. So we can put anything that's combustible into the machine, and if it's a waste crop residue, then as long as it's sufficiently dry, if it's say like above 20% moisture content, then we would want to dry it. And then also the particle size, we'd want typically, like if it was stem waste, we'd want to chip that down to about like 2 centimeters, so that it can flow through the machine and it's got like a uniform size. If it's kind of like all sort of a very wide size range, then that makes it a lot more difficult for us to control the feed rate. So we're trying to achieve the most uniform feed specification before we put it into the machine. So with minimum moisture, minimum ash content, maximum calorific content to get the best outcome. But yes, it can use anything that will burn. Great.
And maybe for Mary and Juma, I mean, are there optimum fuels in terms of the life cycle analysis that you would recommend, or is it all also dependent on obviously what's available in the area?
What's available is obviously the first consideration, and from a sustainability perspective, you don't want to be taking away biomass from perhaps something that would be going back onto the land and maintaining soil fertility, or something that might be used already locally as a free resource. From the life cycle assessment perspective, it's always better to be able to demonstrate that the biomass is a waste rather than a co-product or a byproduct, because you then have to allocate emissions and impacts associated with the feedstock production. These are the rules of life cycle assessment. No. Jim, I don't know, from the economic perspective, I think would be about cost. So again, if something's a waste, one would assume it's not going to cost anything. But then as soon as you start to give something a use, then it starts to have a value.
Starts to have a value, exactly, yes.
Yeah.
In terms of fuel, I think it's quite clear that we would obtain some middle distillate range fuels, kerosene or jet fuel type. And again, we got to optimize the process for local conditions to generate the maximum economic value out of the process. Also, Simon mentioned that about the commodity chemical production from bio oil. So pyrogenesis process could be at the heart of the whole flowchart development, and we could look at the various options of bio oil upgrading from fuel production through to chemical production.
Sure, thank you for that. So we're already overrunning by quite a long time. So we will finish this session in a couple of minutes. Before we do that, I'd just like to ask a couple more questions to Laura and Hilawe. So Laura, we're hearing a lot about right to repair laws coming in the UK and elsewhere. Does that mean that everybody is going to have to end up adopting the sorts of technologies that you're developing for your batteries, where you can repair them and give them a future life?
Yeah, I really hope so. So as far as I understand, with the current right to repair, they're not going so far as to include products that would include batteries. However, hopefully that will change and soon include those type of batteries, because it's type of incentives like that need to be put in place to allow us to address this waste initiative, the large amount of waste we're going to have. So yeah, really hopefully things like that will start to help.
Great, thanks for that. That's encouraging. And finally, for Hilawi, you've done a huge amount of work on the practical side of things in the communities in Ethiopia, where obviously we hope that all the technologies that people have been talking about today are going to be implemented and going to have impact on those communities. From the work that you've done, have you seen anything to suggest that these technologies, these approaches are sort of only particularly appropriate for Ethiopia? Or do you think that from your work that they could be generalizable to much of the rest of sub-Saharan Africa as well?
Thank you, Bernie. I think my experience, from visits to different parts of, sub-Saharan Africa, I think the end users and the problems associated to it is more or less the same. So technology solutions, they might actually need some sort of policy or regulatory adjustments, and which might be slightly different from one country to another. But in general, I think that technology and the resource has very much relevance, because in this countries, biomass is already in use in huge quantity, or the main source of energy is biomass. So this helps to really use the resource in a more efficient and clean manner. Maybe, to answer some of the questions, like, extending the batteries and the right to repair laws, we don't have them. Maybe these are the things that would come up, as the use increases. So, but, my answer to that is yes, it does have relevance to many countries in sub-Saharan Africa.
Great, thank you very much for that, and I'm sure we all hope to see these technologies having that impact in the near future. So with that, I'm afraid we're going to have to wrap up the Q&A session. I will just end by thanking once again the speakers that we had on today's webinar: Simon Ngifose, Andy Gill, Christiani, Scalda Ferry, Mary Black and Juma Sarukan, Hilawi Tasema and Laura Aston. I'd like to thank you all very much for the time and the fascinating presentations. Thank you very much to all of our attendees for listening in and asking some very good questions. Anyone whose question we didn't get to answer, we'll be answering some of those by email later on. If you want to make contact with any of the organisations that have been presenting today, please do send us an email after the webinar is finished. And if you want to see any of these presentations again, they will be archived on the Pyrogenesis website, and the presentations and the video will be up in a couple of days' time, although they won't be up immediately. So thank you very much for your time today, and we look forward to seeing you on our website or at another webinar again very soon. Thank you very much, everybody, and goodbye.